Hi, Chris Guzmal here. We're now going to go through and do a summary of all of the code that we've written involving quicksort. This is the main class in which I create some error variables, pass and fail. And these error variables are static and they're meant to count up the number of test cases that pass and the number of test cases that fail. In a previous video, we've seen that all of our tests pass. And here's main. Declared in the usual way, and a hello world that gets printed out. We invoke a sequence of methods called partition test 1, partition test 2, and so on, all the way up to partition test 8, and then print out how many of those tests passed and how many failed. We also have a partition test 0, which I don't know. Oh, as you may recall, we wrote a partition test for an array of size 0 and realized that it was potentially fraught because we had to figure out how to do the indexing. We accessing out of bounds seemed likely, and so we abandoned that. It might do to go back and find out whether or not partition test 0 succeeds, but it remains sitting there as sort of a to-do for later on, but doesn't seem to be critical. Then we did a sequence of tests, and the test code is actually, I think, overall more sophisticated than the actual sorting code. Partition test 1 is not particularly sophisticated. We just create an array of size 1, set the indices to 0, and proceed to invoke partition. And everything is copacetic because partition with arguments doing a partition on an array of size 1 doesn't actually make sense. It almost doesn't make sense. I mean, partitioning it should result in the original array. We check, and this sort of serves as a test case for our method called same, which compares whether or not two arrays are the same, and increments pass and prints out if they're not. Partition test 2 does a slightly larger array, and when you partition an array of size 2, the result should be sorted. And so that's the expected value here on line 43. Partition test 3 does a slightly bigger test with 3 elements, and it should shove the 3 and the 0 somewhere to the right. And in fact, I would think that we would allow 0, 3. No, I'm sorry. What am I thinking? Oh, the thing is, this test is a little counterintuitive because you might imagine that we're partitioning the entire array. We're only partitioning the first 2 elements of the array, and so 3, 1 becomes 1, 3. It's the only option. I created 2 expected values because I thought that my brain was thinking that I had to account for 2 possibilities for partitioning because I was thinking of partitioning an element, the first 3 elements of the array rather than the entire array. Partition 4 finally starts to become a little bit more sort of intuitive to what a partition is supposed to do because we're talking about partitioning the entire array 3, 1, 0. And what that means is we're going to pivot on the 3, and so the 3 needs to be, everything of value 3 and larger needs to be to the right of everything less than 3. And both of these cases, both of these expected values are acceptable, and it hopefully and does pass that. And then we start to get a little bit more, even more substantial here. Again, we're partitioning on 3, and the expected result's going to have 1s to the left of the 3, and the 4, and the 5. But the 3 could be anywhere. And in fact, we don't have all of the possible acceptable partitionings here. We just have 2 of them. But because of the way the code is implemented, this is sort of acceptable. You might hope for a slightly more robust test case. This test case could produce a failure when a partition nevertheless does what it's supposed to do, but you know, we have to be forgiving of ourselves here. I mean, another thing that we can beat ourselves up on is it just seems like we're doing a lot of replicated code here. Each one of these partition tests seems to be virtually identical to the next. A super clever coder would probably be able to make partition tests 1 through 5 sort of have more code reuse, but I'm going to be kind to myself. Partition test 6 is our most sophisticated partition test. It creates an array of size 100 and then initializes, making it so that the even elements of the array, and that's what this indexing does, 2i, makes it so that that index is even. And so all the even values are determined by this function, which is a random value which maxes out at 50. And then here, odd values of the form 2i plus 1, that's always going to be an odd value, are going to be 50 more than that kind of thing. And so there, because the maximum for this guy is 50 and this guy starts at 50, the general idea is that we're going to specify a number, an exact number of values that are greater than or less than 50. And so if we set the 0th element of the array to 50, then we'll partition around this thing, this distinction that's drawn, and then we'll be able to predict that exactly 49. Remember, the pivot element itself is not necessarily going to be to the left in the first 49 elements, or the first 50 elements. And so as a result, we have, like I said, a pretty sophisticated test here. And conceptually, I would say that's probably the most challenging piece of code of our whole set here. And partition test 7, finally, I don't remember why I did partition test 7 or partition test 8. They were involved, actually they were created as part of debugging quicksort. So when after I did partition test 6, I thought partition worked. Then quicksort failed, and it failed on specific cases that were represented by partition test 7 and partition test 8, which revealed bugs in the quick test code, which we quicksort code. And so the benefit, the thing that you reap from having discovered bugs in your code, is you get additional test cases to demonstrate the robustness of your code. And also as a reminder that, you know what, I thought I had done sufficient testing. I mean, after all, that sophisticated first early test was partition test 6 seemed like it would account for the most egregious scenarios, and the simple scenarios seem to be taken care of by the earlier ones. So what other possible test cases could there be? Well, partition test 7 and partition test 8 were just that. The toString method iterates through our array AR and prints it. A little bit of declaration of an open square bracket at the beginning and a closed square bracket at the end. The same method iterates through 2 arrays simultaneously and checks to see whether or not their corresponding elements are equal. And finally, we get to the partition method itself. Quite a bit of commenting here. We have an input that's an array into integers. There's no actual output, but that's not actually true. We return the index that separates the larger from the smaller values. What I would have written earlier would have been that what we return is the index of the partition element when the method is done, but that's not actually true. That's corresponding to some bugs we were talking about before. And the effect is that it modifies A so that every element less than A of P in the range of P to R appears before to the left of the array. The element greater than or equal to the left of every element greater than or equal to A of P. And so there we go. And here I had a discussion about why a test case failed. I guess I'll leave it in here. I'm a little torn. You know, when you're commenting code, you don't want too much distraction. So I'm going to go ahead and delete this a little bit reluctantly because I'm a kind of a hoarder, but I think I have enough commentary. And I have worried about this, but we have enough test cases now that I'm feeling more confident about partition. So I'm going to remove this comment that indicated that I was worried. I do hate the naming here. I'm going to leave that comment in because as a to-do for later on, we probably should. And then what we do, just to summarize what the method does, is it sets indices I and j at the beginning and end of the range of the partition that we want to perform, which is this P and this R. And then what it does is it squeezes I and j down. It takes I, this increment and decrement is actually a little confusing because it's going to make I keep getting bigger. Actually, you know, this is right. I keeps getting bigger and j keeps getting smaller every time we iterate through in this while loop. Sometimes j and I increment yet again if we have a disagreement about the size of disagreement. If either A of j or A of I is out of place with respect to what the pivot is saying. And if they're out of place, if either one of them is out of place, then we're going to, and if I is less than j, actually that's not true. When they both become out of place, that's what happens. This while loop iterates until we definitely know that j is out of place. This while loop iterates until we definitely know that I is out of place. And then we're going to swap the elements, assuming that I is still before j. And if I is not before j, then we have finished doing the partition, and we return j, which is a legitimate index of the separation between the elements smaller than A of P and the elements larger than A of P. And that's the entire partition method. Swapping does our standard idiom for swapping, and that's the entire partition code. Quicksort then becomes super easy. Super easy to implement. Here we wrote some quicksort test code that all that it does is it creates a small array 3141 and an array that's sorted, and then invokes quicksort on the array to be sorted, and then compares that array to the expected thing, and then we do it for a somewhat larger array. And that's all of our test cases. So I suppose we could do a much bigger, more robust test, but I felt pretty confident that this result was decisive in showing that our quicksort works. What does quicksort do? Now notice I have a bunch of code under quicksort. This code is copied and pasted from the other REPL. And this actually raises a second issue. We were talking about a desire for having debugging in order to not have messy printfs. Here we want to, we ran into a problem actually where I discovered a bug in the partition method, and I fixed it here. And see this I minus j plus plus, which seems very counterintuitive. Why would you increment I, why would you decrement I and then almost immediately increment it? And same thing with j. And it turns out that we want to, at this point in the code, increment I and decrement j on each iteration of the while loop, but it would be super clunky to kind of make it so that that didn't happen on the first iteration unless we do what's on line 70. Corman Lises and Reves do, maybe in the text they describe why they do this, but they do this too and kind of hide it in the way that they implement their whiles, making the pseudocode say do blah until, and a while does. So the thing you're doing is this, and the until is this, but the until means that you are always going to do this at least one time, while a while loop does not guarantee that it's going to execute on its body anytime. So another way of thinking of it is there's iterative loops, structures that sort of are guaranteed to do at least once, sort of like you guys do at least once, do while at least once, or actually the keyword is until. Very few people I know use a do until loop. I do believe they exist in some programming languages, and in fact, maybe it even exists in Java. I'll have to look that up. With that said, my point here is that this is a little bit confusing, this indexing, and I actually got these backwards. I had what was on line 70 backwards with line 72 when I went back and did the updated fix over here. And so I had line 172 and 175 swapped in the REPL that implemented just partitioning, but in the main, in the REPL for quicksort, it was correct. And so I had created a discrepancy between the partitioning method in one place and the partition method in another. Which version of code was the right one? I really was not properly controlling my versions, and what would be ideal would be to have some version control tools, and GitHub is one example that works out for you to help you avoid making that kind of mistake, or if you do make that kind of mistake, it makes it easier for you to detect that kind of mistake. In any case, the good news is that this here partition simply does increment I and decrement j until there's a need to swap and continues to increment I and decrement j until a of I and a of j are both out of place with respect to the criteria for a partition, which is to say big stuff to the right, small stuff to the left. You find a big thing to the right and you find a small thing to the left, then you swap them. And actually, you find a small thing to the right and a big thing to the left, and you swap them, and then you keep looking for pairs of elements that are out of place until the search meets in the middle, as it were. And so that's sort of an intuitive explanation for how partition works. But we already knew that. The question is, what does quicksort do? And what quicksort does is it sorts a region of the array, starting at start and ending at end. And our mnemonic is that AR of start has to be a valid value, and AR of end has to be a valid value. And that tells you where the start and end are in I think, a much more intuitive way. Very frequently in Java, the start value is indeed A of start is the first element, and A of end is one past the right place. And that's, I don't know, I just find that confusing as a convention. So I do it a slightly different way. If the start is greater than or equal to end, then we're going to return, because that means that our array is sorted in that non-existent region. And then we establish what the pivot is for the array by doing the partition on the whole region from start through end. And that pivot then tells us that everything from start to pivot in the array is perfectly less than or equal to everything from pivot 1 to end in the array. And that means that if we were to do a quicksort on the first part as defined by start and pivot, and a quicksort on the second part as started defined by pivot plus 1 and end, then the whole array would in fact be sorted. And so this is a recursive definition of quicksort. A fun extra exercise, which we will probably create a video for, is how do you make this so that it doesn't do a recursive invocation, but instead does iterations. I will tell you that any decent compiler should be able to make an efficient transformation of this to that iterative form. And so some people would argue that you don't need to we don't need to do that, okay? But I do think you need to learn to do that. And so I hope that you kind of understand that distinction. At a minimum, what I'm saying is that transforming this to an iterative code is a valuable exercise for your comprehension of algorithms. And so we'll do a video on that. But that's quicksort. Quicksort's so super easy, so super straightforward. Once you've debugged your partition, and once you've written a whole bunch of test code to make sure things are correct, and then discover you still hadn't found all the bugs, and add a couple more test cases to debug things. And that's what coding is like. There's always more to do, and you can always make it better.